Hello, this lecture will be going over your three-thread lathe program that you'll be doing. At the first glance that you're going to see, there's the big obvious issue are the units that the print is in. Please take note that all the dimensions are in millimeters. So once again, you can kind of decide on what you want to do as far as programming in metric units. My suggestion would be to convert this over to inch units by using the 25.4 conversion. That way when you go ahead and you start making your part and you need to measure it, you have all the tools and you know the dimensions that you need and the tolerances and stuff like that. So that'd be my suggestion as far as the inch versus the metric units go. So regardless of what you're going to do, you're going to program it the same way. So we got a number of threads we're going to do, and this is going to be your first program that you're going to make threads. The first thing you want to keep in mind here when we do that is you want to program the mean dimension for the major diameter. Okay, so you're going to get a tolerance. You're going to get a low limit and a high limit. You look up in the machinery's handbook. You want to find out what that mean dimension is, or the average of those two. Okay, it's important to do that because that gives you that plus or minus tolerance. Okay, you never want to go to the high limit. You never want to go to the low limit. You always want to shoot for that average, and that way, if you are off a little bit, you may be at one of the high limits or low limits, but you're still within tolerance. So you want to go ahead and figure out what that is. Find all your dimensions. You might as well get your pitch diameters when you're looking up in the machinery's handbook. You don't need that for programming, but you do need that for actually making a part, obviously. Well, one thing you're going to be doing here, you notice that these chamfers here on the back side, okay? So this is going to take a little bit of calculating. This is going to be done very similar to what that groove exercise was, as far as the you had to create your G75, your grooves with your G75s, and then you're going to come back in and you're going to finish those grooves and put those chamfers in with G01s and G00s. Okay, so we're going to go ahead and do that. Now, remember, let me see if I can blow this up a little bit more. Okay, so remember the way we do, that's our threading insert. We calibrate this corner. So that's what all of our dimensions are coming off of. So the G75, you're going to do basically this groove. Okay, if you want to leave a little stock on here, 5 thousandths like we did with that groove assignment, that'd be fine, because you're going to come through and cut that anyway. So you have that done with your G75. And then now with your G70, or with the G01s, basically what you're going to do is you're going to come down to this point. You got to remember you have to take into account your width of your tool. Then you're going to put in your 45. Then you'll be here, taking into account of your tool, G01, G01, and then wrap it back to your next one. So that little bit of a chamfer you can just take in one pass. So like I said, you want to stop, obviously off your part, feed down to this point, down to here, and then finish that groove. All the while, keep it in mind that this is the corner of that tool that you're doing. So that would take care of your grooves. And maybe I got ahead of myself just a little bit, but before those grooves, you're also going to be cutting that profile out like that. Now this project here, we're going to be using cutter comp. This will be the first project that you're going to use cutter comp on, and it actually makes it cutting those chamfers and everything a little bit easier, because all of a sudden, unlike that last assignment that we did, the machine will do all the calculating for you where that tool nose has to be for each specific tool nose radius that we put in the offset page. So I want to go back into our manual. And on page 67, they start talking about it. So with tool nose compensation, first thing you need to do is your approach move and your exit move or canceling your cutter comp. Okay? Maybe a little jump ahead a little bit. First thing you have to decide is what kind of cutter comp you're going to use, G42 or G41. The concept works the same way in determining what's G42 or G41. You got to visualize yourself from behind the cutter as the tool's cutting away. Do you want to be on the right side or do you want to be on the left side? So if you could picture yourself, if this is your part, this is the operator side. Okay, that's an O. This is the operator side. So in the case of a manual lathe, your tool is coming from this side. Okay, but on the CNC or most of your slant beds, your tool's coming in from the back side. So that's in our case with our Haas ST10s and ST20s. So that tool's coming down, it's coming over and it's cutting away from you. You want to be on the right side, which is going to give you a G42. Now if you would be boring, if you had an inside feature in here and your tool was inside here, that's a pretty rough tool. As that tool is cutting away from you, now you want to be on the left side, so it would be a G41. So unlike the mill, where pretty much every time you're cutting, you want to be climb milling, you're going to be using G41. On the lathe, you could be using both of them. A lot of times you use two of them, or each one, within your same program. So once you determine G41, G42, you have your approach moves. Okay? Let's see, did I jump ahead too far? There we go. So your approach moves. Now this is going to be done inside your can cycle, your 71 and your 70. So you have your G71, P1, Q2, and U, W, D, V, or I mean F for feed rate. So that cutter comp wants to be applied in your first two lines. Okay, can it be applied down here or at the latest as it goes into Z0? Okay, so those first two lines you want to apply your cutter comp. And then when you're done, you want to make sure you're off your part and then do your G40. You never want to turn on your cutter comp or cancel your cutter comp if you're within your part, because it could be making some moves to cancel that cutter comp that would scrap your part out. So you want to make sure you're off your part completely before you turn on your cutter comp, and the same thing before you turn off your cutter comp, cancel it. So we'll just jump ahead to an example that they have in the book. I'm going to come back to that in a little bit. I'll try to find one here with. Okay, so here's an example. Page 80. It's going to cut out this part like that using cutter comp. Okay, so here's their example in their program. Okay, G71, P112, Q125. So that's there should be end lines, and looks like I got a misprint here. That should be a 13. And I'm going to guess this is going to be, nope, the 125 is right. And we have our U, or W, D, or V. Okay. N113, G42, G00, it can be done in a rapid move or a cut move down to our first X dimension. Okay. So that applies our cutter comp. And from there, it's just all print dimensions in. You don't have to worry about two nulls or anything like that. Now notice here, they're off their part, and then they go ahead and cancel their cutter comp. Okay. And you cancel it out at that X to that same point that they started. Okay, so it's as simple as that as far as writing your program. You just turn it on in the first couple lines and you turn it off in the last line. So I want to jump back. So when you set up your machine, you have to tell the machine where the tool is coming from. This is something different than the mill, just because there are many different variations of tool holders. whether it be boring, center cutting, just normal turning with a right-hand tool, but you have to tell the machine the tip direction that that tool is moving, and then that's how it determines to offset the tool nose radius. So each one of these, you're going to actually put in the offset page, there's something in there that just says tip. Okay, that's a tip direction. This is going to be your most common. Turning the outside of your tool with your tool cutting this way. Now this is for a slant bed lathe like we have for our CNCs. This one here would be for like your manual or what they call tool room lathes, where your tool is standing on the side that you are, the same side you are of the part. But this is done here for us. We use that in boring. So if you could picture that tool inside of a part, cutting out the bore with that tool coming from the back. But this is where our normal outside turning is. So in the offset page, you have to tell it which tip direction. Now, if you use the default or the 0, it actually undercuts your part by twice your tool nose radius. So you want to make sure you change that off of 0. Now, you only have to do this with tools that use cutter comp width. So along with your tool nose radius that you have to punch in, whether it be a 15 or a 31 thousandth tool nose radius. So that's something you got to remember to do when you do your setup. So that's your cutter comp. So the other thing we have to do is we have to cut these threads. Okay, so in your manual, I believe it's around page 112. Is where you're going to cut out your threads. Okay. So inside a G76, you can use this for OD or ID thread cutting. You need your X, and it would help if you don't have notes on from your programming classes. You might want to write these down. Your X is going to be your minor diameter. You need your Z. That's just a simple how far is it moving? How far does the threads go? Okay. And then you need a K value, which is your thread height. You need a D, which is the depth. And for this, if you always use 3 to 5 thousandths, you'd be pretty safe. And then you need a feed rate, and your feed rate needs to match your RPMs. Now it's a little bit simpler in the lathe than it is the mill because we feed in per revolution. So your feed rate is basically going to be 1 divided by threads per inch. Now that's for inch units. I think I'm going to run out of space. That's for inch units for feed rate. For metric, it equals your pitch, which basically that's what it is, 1 divided by threads per inch. Okay, so you need those codes inside your can cycle. So we'll jump ahead to an example here. So in our example here, we're going to be cutting a 3/4 16. Okay, so you're going to wrap it to your start point. Okay, you can do this normally. For some reason in the example of the book here, they go to Z1 inch, and then down here you notice they go to Z.2. I don't see no reason why you shouldn't just go to Z.1 right away. The X stands for the nominal thread size. So we have 3/4 16. Okay, so 3/4 would be 0.75. Now remember, this should be turned down a little bit smaller than that because of your major diameter is not 3/4 inch, or at least it should be. For some class of threads, the nominal size may be the higher limit, but either way, you should be just below that 3/4 of an inch. So that way you're not going to be scraping across your part when it returns back to the start point. Then you call up your G76. Your X is your minor. Okay, Z is the thread depth, how far is it traveling, and your K is the height of that thread. Okay, and then we have our D. Like I said, if you could use 3 to 5, that'd be great. And then here, that is 1 divided by 16 is equal to 0.0625. Okay? But that K value, what does that K value stand for? And I'm going to jump back up here. So that K value is a thread height. So basically where you come up with that is your nominal size minus, minus your minor diameter divided by 2, because it's a thread height. So you're taking your nominal, which is here, minus the minor, but you're dividing it by 2 because these are in diameter form, and we want radius value. So if you go back to our example, so basically if you took 0.75 minus 0.674 and divided by 2, you would end up with 0.038, and that gives you your thread height. So from here you just kind of, in your case, you're going to wrap a G00 out to an X and then a Z, and then do another G76, do your 3 threads. Okay, so you do that, so you're going to have G76, it'll do these threads, you're going to wrap it up, wrap it over, oops, not that far though. You can wrap it up, wrap it over, it'll do these threads, wrap it up, wrap it over, do these threads, and then you're done. Okay, so you're going to have 3 G76s inside your program. So one thing you want to keep in mind that when you calibrate this tool, if it looks something like this, you're calibrating this edge and obviously this edge. So when you do this, when you figure out how deep you need to go with that thread, you just want to stay, in this case, just shy of the 40 millimeters. So if you stayed a half a millimeter shy, so 39, 39.5, you know you'll cut your threads all the way through here and you won't crash. And that's why you typically do calibrate that side, because you can go right up against the shoulders without worrying about crashing. So, well, that's kind of the overview of the 3-thread project. Good luck on it, and if you have any questions, please come and see me.